Okay. So for chapter 6, this is the kind of stuff we have so far. These are all the important equations that I can remember. This is the Schrodinger stuff. Negative L, -1, 0, +1, plus L. And this gives a orbital orientation. Or shape, if you will, whichever you want. That's it for chapter 6.
Yeah.
And what are the constants? R is 6.626 times 10 to the minus 34. Oh, that's not R, that's H.
Yeah.
Joules seconds. R is like a 1.0974 times 10 to the 7.
Yeah.
And C is 2.998 times 10 to the 8th meters per second.
Right.
That's just a quick review of all the things you need to know from chapter 6. Well, not all, but certainly the meat of the dinner, right? Unless you're a vegetarian, then I would say the protein of your dinner.
Yeah.
Because even though you're a vegetarian, you should still manage to eat some protein. Some sort of beans and some sort of rice. You know why?
What? Why?
Beans and rice.
Why beans and rice?
Because neither is a complete protein like meat is.
Oh.
So they're complementary in that if you eat both, you will get a complete amount of protein. And if you think about ancient civilizations, they all eat beans and rice. And you know the ones that didn't? Well, they weren't getting their complete protein, so they didn't survive.
Okay.
That's funny. Some of my favorite dishes are beans and rice. Okay. What more detail do you want from chapter 6 before we move on?
I think that's it. I just wanted to be sure I had everything covered.
Okay, chapter 7 is about what?
Electron configuration.
Okay, that's a big part of it. So when we talk about electron configurations, there's the SPDF method. Right, where you use that block method. I should call it the SPDF block method.
Yeah.
And you should be able to do that. There's the real configuration.
Real.
Yeah, what we find out experimentally.
Oh.
And does the real configuration always match the SPDF configuration or vice versa?
No.
You're not responsible for knowing the real configuration, but if given, what should you be able to do?
Determine the element.
You should ID the element. What else?
Predict the SPDF.
Predict the SPDF on the block method. And what else?
I don't know.
You should be able to give a reasonable explanation for why they're different.
Right.
Okay, you should also be able to get the electron configuration of atoms, cations, and anions. Sound about right?
Yeah.
And for cations, what do you do? For atoms, we just use the block method. For cations, what do you do? Well, you count electrons, or actually, you get the atom using the block, then take away electrons, right?
Yeah.
Take away the least stable. Now, if anything, for the atoms, we should probably mention that with the block method, sometimes you have to rearrange. And so I'm going to put my little pigtail there. For anions, it's usually same as the noble gas. In the same period. And when we look at ways of writing the electron configuration, you've got the SPDF method, you've got the noble gas SPDF method, and then you've got the noble gas orbital box diagram, right?
Yeah.
And what are the two things we should say about the orbital box diagram? One is you use Hund's rule to fill, and you use the Pauli exclusion principle.
Yeah.
And you might think, well, where are we using the Pauli exclusion principle? And the answer is every time you put only 2 electrons in an orbital, you're using the Pauli exclusion principle.
Right.
That's why you don't stick 3 in there. What else do we do in that chapter? It's chapter 7.
I don't know. I feel like that's it. But there is more.
Oh, yeah, there is.
I just feel like, oh, periodic trends.
Periodic trends. There you go. And so these are trends where we look at the period trend. So that's in a row, correct?
Yeah.
And essentially, what is the reasoning for the trend? Not the trend itself, but the reasoning we look for.
What do you mean?
The reason to explain why the trend is the way it is.
Well, I mean, it depends.
Why is lithium larger than beryllium when beryllium has more electrons?
Oh, because it has more protons,
Okay, so you should know that
more or less.
the protons kind of explains the trend, right?
Yeah.
But what about for something like nitrogen and oxygen? The first electron to take from oxygen is actually easier than nitrogen when oxygen has more protons.
Yeah.
What was the explanation there?
Paired or unpaired.
Okay. And we also look at group trends, right?
Yeah.
And what was the explanation for the group trend?
Shell.
Shell. So
Larger.
um, of course, these reasons are way too brief, even for the asking of give a brief explanation.
Yeah.
You know, if you wanted to expand on the shell number defining the group trend, what would it be?
Larger shells. Electrons in larger shells are easier to remove.
Yes, that would explain ionization energy. It would also explain electron affinity, right? That when they drop into a larger cell, they give off less energy.
Yeah.
What about for size of the atom or the ion?
The larger shell, the farther apart the electrons are,
And therefore,
making them larger.
okay. What about cations versus anions?
Cat ions have less.
Actually, that would be up here for this one right here, but let's go ahead and jump up here. For the periodic trend, why are cations in a period smaller than anions in the period?
Cat ions have less electrons.
Actually, it turns out it's shell.
Huh?
It's shell. Lithium ion only has electrons in the first shell. In the same period, oxygen has electrons in the second shell. So why is an oxide ion so much bigger than lithium? Shell. So this is a place where shell might be used to explain something.
Yeah.
Okay, so we use shell number basically when we look at the group trend, don't we?
Yeah.
What are the 4 trends that we looked at?
Atomic radii, ionization energy.
Hold it. Let's stay with radii. Atomic radii,
And ion
radii.
radii.
Unless you want to say radiuses.
Radius.
Then you said ionization energy. And what's the 4th one?
Electron enthalpy.
Electron attachment enthalpy. And when you take the absolute value, we call that electron affinity.
So the former is negative value.
This one, yeah, negative.
Okay.
So the absolute value, of course, is positive.
So if you ask us on an exam, we need to be careful to pay attention to which one you're actually asking for.
Yeah.
If we're gonna throw a negative on there or not.
Yeah. But the beautiful thing is if I asked a question about which has the greatest difference, it doesn't matter whether it's negative or positive. Negative 50 versus negative 100 is bigger than negative 75 and negative 100, right?
Yeah.
And positive 50, positive 100 is bigger than positive 75, positive 100. So if I ask what shows the greatest difference in energy, then it doesn't matter. You can approach it from either way.
Yeah.
I'm not really fond of the way the author has defined these things. Because again, I understand and I like energies being negative and positive, but I think we need to focus more on what the negative and positive mean rather than just attaching sign to it. We attach sign to it for a reason. And what's the reason? Negative is energy released. Positive is energy absorbed. That is the definition of why something is positive or negative. So positive and negative is actually a simplifying of what's actually happening. And the reality is it's about whether it's being absorbed or released. And that's more important to me than, oh, is it positive or negative?
Okay.
So I'm like that a lot in these chapters where I'm okay with negative numbers for things like wavelengths. What's a negative wavelength? Oh, it's one that's being emitted. What's a positive wavelength? One being absorbed. And a lot of books make sure that you only calculate positive wavelengths, which to me takes away sort of the meaning. It's kind of like a percent error. For percent error, I like positive and I like negative, because positive percent error means your value was too large, and negative means your value was too small. Pretty simple, but informative. Okay, so I think these are the big ones from chapter 7, if I remember correctly.
Yeah. Magnetism.
Magnetism. That one's pretty easy too.
Mhm.
So what are the 3 types of magnetism?
Para, dia, ferro. I don't know.
Right. So tell me what paramagnetism means or what it is.
Unpaired, and they attract.
Attracted to a magnet. That's what it is. And you already told me how it is achieved. Unpaired electron or electrons in an orbital or orbitals, right?
Yeah.
So what about diamagnetism?
All
What is that?
they're all paired and they repel.
Repelled by a magnet. And it's just slightly repelled by a magnet. And all paired electrons in orbitals. And then what's ferromagnetic?
A paramagnetic element that, I don't know.
That can be made into a magnet.
Okay.
So I'm going to say paramagnetic substance that can be magnetized. And basically, to make a magnet out of something, you take that substance and you put it next to a bigger magnet, a big magnet. And what the big magnet does is it makes all of your spins align. So just because you have a paramagnetic substance doesn't mean that all of your electrons are spinning in the same direction, in the same orientation.
Right.
But when you put them against a larger magnet, they do all have to align themselves so that they're the most stable spin versus the large magnet. And then when you remove the paramagnetic material, if all the electrons kind of just go back to whatever they used to be doing, that's great. It's no longer magnetic. But if they stay in that orientation, it's magnetized. So iron is a great example of something that can be turned into a magnet. Now you got to imagine all of these electrons that are all aligned in the same orientation, they're on different atoms, right?
It would have to be.
Yes. And having them in the same orientation isn't really that stable because they repel one another.
Yeah.
But what enables them to do it is that they're on different atoms.
Okay.
Okay. I don't know the reason why some of them just go back to normal and don't stay aligned, but a lot of materials don't stay aligned. So how is it that you can take something that you magnetized, like we did this in a, are you okay?
Oh yeah, I just sneezed.
Okay. So if when I was a kid, we magnetized paper clips on a big magnet. The teacher brought out this huge magnet and we all rubbed our paper clips on the magnet to magnetize it. And to show that it was magnetized, you take your paper clip and you put it on something that was metal and see if it stuck. And it worked. But the teacher also said for that big magnet, you need to be careful with this because you can actually take a magnet and make it not a magnet anymore. So what do you think are the two most common ways to make a magnet not a magnet anymore?
I don't know.
Well, all those electrons are aligned, right?
Yeah.
How do you get them unaligned?
Take them away from the magnet.
What's that?
Take them away from the magnet.
You can't take them away from the magnet.
I don't know.
Drop it.
In that, oh, how would that change it?
Well, they are electrons, right?
Mm-hmm.
How tiny are electrons?
Very tiny.
Very tiny. So if you drop them, drop a magnet, would that be perhaps enough energy to disrupt the orientation of the electrons?
Yeah.
Yeah, we're not trying to remove the electron. We're just trying to change its orientation. And when you remove an electron from an atom, it takes a very, very small amount of energy. You saw already that the energy of an electron in the first orbit of hydrogen is minus 2.180 times 10 to the minus 18 joules. 10 to the minus 18 joules. We know that 1 calorie is 4.184 joules, right?
Mm-hmm.
So if you think about it, 1 calorie is enough energy to remove 10 to the, I don't know, I want to say 10 to the 20 electrons. 1 calorie. That's a lot of energy, right?
Yeah.
So how much energy would it take to not remove electrons, but to just kind of change their orientation? Probably a lot less, don't you think?
Yeah.
So you can drop your magnet. What else would be a way to change the orientation of the electrons that are aligned?
Mm-hmm.
So think about this. When we drop it, are we adding energy to the system?
Yeah.
So when the magnet hits the ground, is energy added to the magnet?
No.
Sure it is. If you were to hit a tennis ball,
Right.
would you be adding energy to that tennis ball?
Yeah.
Okay. So the ground is the racket and the magnet is the ball. When the magnet hits the ground, are you adding energy to it?
Yeah.
You bet your bippy. So you have to add energy to get this thing to have its electrons shocked so that they're no longer aligned. So what you should be thinking about here, okay, is if I add energy by dropping it, what other ways could you add energy to your magnet?
Heat.
Heat, exactly. See, that is the sign of a great instructor. I brought you right to the solution by going down to the nitty gritty and explaining this is what's really happening. It's about energy. And right away you picked up, well, I can add energy by heating something. So don't heat your magnets and
Okay.
don't drop them.
So is leaving them out in the sun enough?
You know, I don't know. That's a great question. You might want to test that.
Okay.
I have the feeling that it's probably not, but not enough to instantly demagnetize something, but it might work over time.
Yeah.
Because, you know, with a small amount of heat, you might realign a few of them and more as time goes on. And we know that getting them to align is not really a natural thing or a, how do I say this, or a common thing, because if that were the case, then everything that's paramagnetic should be ferromagnetic right away.
Right.
It's less stable to be magnetized than it is to be not magnetized. So if that's the case, then yeah, maybe sunlight can, if something is magnetized, demagnetize over time.
Yeah.
That makes sense. It'd be an interesting thing to find out. But then you'd have to, you know, have all sorts of interesting things like how do you test the magnetism, right? The strength of the magnetism. So
Right. Oh,
can you think of a way to test the magnetism, the strength of it? Something you could do at home.
I guess by starting with a larger item to see, and then going down in size or up in size.
But how do you test how strong the magnet is?
Well, like if a heavier object can stick to it versus a lighter.
To the magnet?
Yeah. So
You
like
could
if,
do that.
yeah.
I was thinking something like this. You could put your magnet on the refrigerator, right?
Yeah.
Then you could put a piece of paper underneath your magnet.
Yeah.
Then you could put 2 pieces and 3 pieces. And when the magnet no longer sticks to the refrigerator, that's kind of a sign of its strength. The more pieces of paper, the stronger it is.
Yeah.
And then you could test that over time fairly easily because you've got a refrigerator, you've got paper. A very simple scientific way of testing things. So, and that's what scientists do. We come up with clever ways to test things. And of course, once you find out that, oh yeah, sunlight does work, then you find out, well, what do real scientists, as it were, and it's not really real scientists, what do scientists in the laboratory use to measure magnetism?
Right. I'm sure there's some device.
I'm sure there is too. I mean, actually, most of your scales are based on magnets. So it measures attraction. And that's why we're supposed to call them scales and not balances, because balances, you actually balance it versus something else.
Right.
And most of ours are scales. They're based on magnets. But scales also, you kind of get to think like a Lady Liberty with her scales. Okay. What else can I help you with?
Oh, I don't know. I haven't looked at the next chapter yet.
Okay. Well, do you want to look at some of the problems from the next chapter and just do them? I've got time, or if you want, you can do something else. It's up to you. You're the only one here, so You can almost think of this as like a study session for yourself.
Yeah,
Tutoring.
you figured it out, what I, my study group, I found it. It's Tony.
So I'm going to leave it up to you since I do have these questions from chapter 8
Okay,
that are basically the even ones. So how do you answer a question like this? So first of all, can you tell me what a valence electron is?
the electrons in the outermost shell.
Okay, electrons in the outermost. And just to be very specific, in the outermost shell
Occupied,
that has electrons in it.
the outermost occupied shell.
Yeah.
Okay,
So when we take a look at like lithium with an electron configuration of 1s2, 2s1, there it is. When we look at sodium, which is 1s2, 2s2, 2p6, 3s1, there it is. When we look at potassium, which is argon, I believe. Let me take a look. I'm going to noble gas configuration now.
yeah, argon's right.
Argon, 4s1, there it is. When we go to rubidium, which is going to be xenon or krypton,
Krypton.
5s1, there it is. So these are all in group 1A, right?
Yeah,
And the number of valence electrons is equal to 1. And if we were to look at group 2A,
oh, I see.
and we were to look at beryllium, it'd be 1s2, 2s2, and there's 2 valence electrons. Magnesium would be neon, 3s2, and there's 2 valence electrons. Calcium would be argon, 4s2, and there's 2 valence electrons. And strontium, which would be krypton, 5s2, there's 2 valence electrons. So here, for group 2A, you get 2 valence electrons. Now, in group 3A, if we just look at aluminum, and aluminum is neon, 3s2, 3p1, we have 3 valence electrons.
So
And this is aluminum.
is this
So,
trend for all of them?
yeah, if you go through and do everything in just a second period, you find out that the number of valence electrons is equal to the group number.
Okay,
So that's a big deal. Number of valence electrons is equal to the group number. And this is for the main group elements.
okay, not transition,
Pardon me?
not the transition metal,
Right. The transition metals, it's basically 2.
basically.
Yep. Let's look at some transition metals, okay? So let's look at scandium. Scandium is argon. 3d1, 4s2. Titanium is argon 3D2 4s2. Vanadium is argon 3D3 4s2. Now, chromium is weird. The real electron configuration is 3D5 4s1. Manganese goes back to normal. It's argon 3D5 4s2.
I see.
Iron is argon 3D6 4s2. So when we look at valence electrons, we've got 2, 2, 2, 1, 2, 2, and we could keep going. But basically, how many valence electrons does a transition metal have?
2.
2. And if
And
we
it makes
go,
sense.
pardon me?
That makes sense.
Yeah. And then if you look at yttrium, it's going to be a lot like scandium, but instead of argon, it's going to be krypton. And it's going to be 4D1, 5s2.
Right.
So the transition metals that don't have 2 valence electrons tend to be those that are ones that don't have normal electron configurations using the block notation, using the block method for finding them. And it has to do with symmetry, remember?
So for that chromium, would we be expected to know that it's 1, or would we be expected to know that it's 2 based off?
You'd be expected to know that most transition metals are 2,
Okay.
except for the weird ones. And you don't need to know which ones are weird.
Okay.
But you've already been exposed to kind of which are the weird ones, right?
Yeah.
So that helps. That helps if you see something that's weird. You say, "Oh, this is weird, but I know there's a reason."
Right.
Okay. That being said, give the group number and the number of valence electrons for each of the following. So carbon would be in group number 4A, right?
Yeah.
And how many valence electrons? 4. Chlorine is in group 7A, 7 valence electrons. Neon is in group 8A, 8 valence electrons. Silicon, which is right below carbon, is in group 4A, so it's got 4 valence electrons. Selenium, let's see, where is that guy?
6A.
Beneath sulfur, so 6A. And aluminum is in group 3A, right? Oops, this is supposed to be E and then F.
Mhm.
3A, 3 valence electrons. So that's the first one right there.
Okay.
Okay. Which of the following elements are capable of forming hypervalent compounds? So what does hypervalent mean?
I assume more than 8.
More than 8 electrons, right? And the answer is A, no,
Right.
B, yes, C, no, D, no, E, yes. So I haven't answered all of these yet, but what is the difference between these?
Mm,
Look at your periodic table.
I am.
So focus on the yeses. Where are they?
5A and 7A.
So clearly that doesn't matter because F is in 5 or 7A, right?
Yeah.
Okay, so group doesn't matter.
So it's period that matters.
Pardon me?
So period 3 elements are yeses, phosphorus and chlorine
And
and
what about the nose?
mm, they are group period 2.
Yep. So period twos can't.
Why?
Basically because they don't have enough orbitals. The bonding orbitals for period 2 are the 2s and the 3 2p's, for a total of 4 bonds or 8 electrons.
Okay.
For period 3, you've got the 3s, the 3 3p's, and you've also got 5 3d's. So how many bonds could you presumably make here? 5 plus 3 plus 1, 9 bonds and 18 electrons. Now, usually the limit is 6 bonds or 12 electrons. And the reason for that is I want you to think about you being a central atom bonding to things. Could an atom bond to your left?
Yeah.
Could another atom bond to your right without bothering the first atom?
Yeah.
Could another atom come up and bond to you from your back without bothering the other 2 atoms?
Sure.
How about from the front?
Sure.
So you're surrounded on 4 sides because you basically have 4 sides, right?
Yeah.
But you actually have 6 sides. Could another atom come and bond on your head?
Yeah.
And how about at your feet? Okay, so you could be in between 6 atoms. Where would the 7th one go?
I don't know.
You're surrounded, right? So it'd be hard for a 7th one to get in there. It does happen rarely, but not often. So that's why the word usually, 6 bonds. It's a space consideration. A lot of people forget that atoms have a physical character to them. And sometimes it's the physical character that limits what's going on or
Right.
defines what's going on. And so a lot of people forget that because no one's ever seen an atom and no one ever will. So you forget, you have to think about these things in your mind, and then you can model them. You can say, okay, here's a sphere. How many spheres can I put around this atom and have them actually touch the sphere, indicating a bond?
Yeah.
And once you get to 6, getting that 7/1 in there is kind of hard.
Yeah.
Okay, so with that in mind, how about boron?
Boron. No.
How about selenium?
Or I'm gonna say no.
No, it's a yes.
Yeah.
Because in period 4, they have a 4s, 4p, 4d, and 4f, right? Okay, how about tin?
Yeah.
Oh, you're pretty casual with tin. You don't say yes, you say yeah, huh?
Yeah.
Okay, so that's how easy it is to tell which ones are capable of forming hypervalent compounds.
So is it the elements like period 3 and below, essentially?
How about we call it period 3 and higher, 3, 4, 5, 6, rather than 3 and below. Or you could say, looking at the periodic table, it's where period 3 is, and those elements lower on the periodic table.
Okay.
Because if I let something like that stay in video land and people said, oh, but you guys said 3 and lower, that'd be like
Right.
3, 2, 1, right?
Yeah.
So the first 2 periods, the maximum would be 4. For periods 3, 4, and greater, as many as 6. And we're talking bonds.
Yeah.
So if we're talking electrons, in the first 2 periods, the maximum is 8. And really for period 1, the maximum is 2.
Yeah.
And then period 2, the maximum is 8. And then from 3 on up to 7, the maximum would be probably 12. Okay.
Yeah.
Let's take a look at number 6. Draw the Lewis structure for each of the following molecules or ions. So do you remember the rules for getting the Lewis structure?
Yeah, carbon is usually center.
Well,
That's all I remember.
first thing you do is you count valence electrons.
So since this is a compound,
You got a carbon plus a sulfur plus a sulfur. How many for a carbon atom?
4.
Okay. How many for a sulfur?
Is it 5?
6. It's below oxygen.
Okay.
So we have 16 valence electrons here. And then you choose a central atom. And I'm going to put choose central atoms because there will be some cases where we have more than one central atom. And generally, when you're choosing central atoms, you choose the one that tends to make the most bonds.
Right.
Makes the most bonds, or smaller atomic number if in the same group. So like if you had a carbon versus a silicone, you would choose carbon as your central. Or if you had like oxygen versus sulfur, you choose, it's not smaller, larger atomic number. You choose sulfur.
Larger. Okay.
So let's take a look at the number of bonds an atom usually makes. And let's look at group or period 2.
Okay.
So you've got lithium, and there's its 1 valence electron because it's in group 1A. Here's beryllium, and it's got 2 valence electrons because it's in 2A. Here's boron, it's got 3 valence electrons because it's in 3A. And each dot represents a valence electron.
Mm-hmm.
And here's carbon, it's got 4 dots because it's in group 4A. Nitrogen has 5 dots, and you'll notice with nitrogen, 2 of the dots I put side by side, and I treat each one of these elements like it has 4 sides. Oxygen has 6. Fluorine has 7. And neon has 8. And these following are all known compounds of these with hydrogen.
Can you say that again?
These are all known compounds with hydrogen. And I'm going to put, here's hydrogen up above.
Okay.
Now, these are also ways of drawing them.
Right.
Where shared electrons are drawn as a line, which is considered to be a covalent bond. So for the rest of these, they're going to get a little crowded, so I'm going to spread them out a bit. Here's nitrogen. And then oxygen I'm going to do right here. Fluorine I'm going to do right here. And neon, I can't make any bonds to it.
Because it's full.
Well, not because it's full, because, well, yeah, because it's full. It's got an octet. So you'll notice that lithium can be hypovalent, less than 8, right?
Mhm.
Hydrogen can also be hypovalent. In fact, it's always hypovalent. It's only 2.
Okay.
Beryllium can be hypovalent, right?
Yeah.
Boron can be hypovalent.
Yeah.
Carbon has 8. Nitrogen has 8. Oxygen has 8. Fluorine has 8. So they're not hypovalent, they're not hypervalent, they have 8. That's called the octet rule. So if we look at sulfur, sulfur also makes a compound with hydrogen, and it looks like this. So what would we say about this sulfur compound compared to this oxygen compound? They look identical, except for that the middle atom is a sulfur instead of an oxygen, right? Okay. So if we look at the number of bonds these tend to make, it's for group 1A, so for 1A, they tend to make 1, 2A, 2, 3A, 3, 4A, 4, 5A, 3, 6A, 2, 7A, 1, and 8A, 0. Now, if we look at the period, so this is period 2, but if we look at period 3, things are a little different. So I will change some things in here. This can also be 4. So it usually makes 3, but it can make 4.
Right.
Here it's 1, 2, 3, 4, 4, and actually 5A can make 4, 6A can make 1 or 3. For 5A, it's 3, 5, 3 or 5. Here it's 2 or 4 or 6. And here it's 1 or 3 or 7 or 5, I'm sorry. And here it tends to be 0. So except for this 3A where I put 3, 4, when we go to 5A and greater, look at the exceptions. What is the pattern for the exceptions? It jumps by 2, 3, 5, 246, 135. And it
Mhm.
stays pretty much the same after that. So here, this would be 3, 5, 2, 4, 6. And this actually goes 1, 3, 5, 7. And here, this is 0, but I think it can also make 2 or 4. And can you see this even jumps by 2?
Yeah.
So here, if you have 5 bonds, that makes you hypervalent because you got 10 electrons, right?
Yeah.
You've got 6 bonds, you've got 12. Here's an example where you've got 7 bonds, you've got 14 electrons.
Yeah.
Okay, those are unusual.
I need you to draw this for me.
Draw what?
Draw the exceptions.
What do you mean by that?
I don't know, just so I could see it visually. How
Well,
there's-
let's put the atoms in here. So this is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And you can redo this table where you put like lithium here, and here's a 1, beryllium here, here's a 2,
Mhm.
boron here, here's a 3, 4. And you can make it like a periodic table.
Okay.
And it's more helpful for you to do that yourself than for me to just kind of lay it out for you. But here, if we look at period 3, what's after lithium? Sodium, and then magnesium, and then aluminum, and then silicon, and then phosphorus, and then sulfur, and then chlorine. This is neon, and this is argon. But you can build this little table yourself. And in fact, if you look at the Chem 2 book, this table's in there.
Hmm.
I'm not sure that it's in the Chem 1A book.
Okay.
So here, if we go back to trying to draw this CS2, first you're going to count valence electrons. And we had 16.
Mhm.
And then we're going to choose a central atom, and that's going to be sulfur. And once you choose, I mean, that's going to be carbon because it can make more bonds. And once you choose the central atom, you put all the other atoms attached to the central atom, essentially, by a single bond. And then you take your extra electrons and you put them around the terminal atoms like that until you've used all 16 or you run out. But you put octets. And then what you're going to do is you're going to take 2 of these and make them a shared pair. And 2 of these and make them a shared pair. And the reason you do this is because you want carbon to have 8 electrons. You can't just throw more electrons in there, so you have to move the electrons around that you have.
Okay.
So carbon likes to make 4 bonds. Here it has 4 bonds. This sulfur likes to make 2 bonds. Here it has 2 bonds. The other sulfur, same thing. So that's CS2. And then for BF4 minus, if you count electrons, you've got 3 for boron, plus 4 for fluorine, plus 1 for the negative charge.
Right.
So that's 8. You're going to put boron in the middle because it normally makes 3 bonds and fluorine makes 1.
So we have 4 fluorine. Okay. Okay.
Now remember how on that chart before
Yeah.
I put down that boron makes 3 bonds, but it can make 4.
Mhm.
Well, here it is, making 4. Now this one we're pretty much done, except you have to do this. Whenever you have an ion, you put a bracket around it and a charge on the outside.
So we
Now
don't,
notice this HNO2, the arrangement of atoms HONO, like you're surprised. Oh no. Okay. So HNO2, you got 1 plus 5 plus 2 times 6. So that's 18 electrons, right? And they say make the arrangement like this. HONO. So we put lone pairs on oxygen and lone pairs on oxygen here. And if you count these electrons, this happens to be 16.
yeah.
So we put a lone pair on nitrogen.
So it has 3.
Yeah. So you might be wondering, why did I put lone pairs on the oxygens before the nitrogen? And the answer is for now, we're going to say that you put the lone pairs on the one that has a higher, that you expect to have a higher electron affinity attachment. No, what is it called? Electron attachment energy.
Okay.
Okay, so here, can you see that we don't have the number of bonds we like on nitrogen, and we don't have an octet?
Yeah.
So here are our 2 choices. One is to do this. And the other is to do this. So which choice do we like better, number 1 or number 2, and why?
Maybe number 2. It's more symmetrical.
No, it has nothing to do with symmetry. Number 2 is correct, but
It looks better.
we're going to approach this from the only way we have of measuring it is how many bonds do each of these atoms like to make?
Right.
How about hydrogen?
Oh. Oh, hydrogen makes 1.
How about oxygen?
It can make 6.
Nope. Oxygen's 2, 1, or 3.
Oh yeah,
So how many does it like to make? 2.
2.
Nitrogen likes to make 3. So here we have oxygen making a 3 and oxygen making a 1, but those are in parentheses, which means they're not the most common.
Right.
Here the oxygen's making 2, here the oxygen's making 2. In both the nitrogen's making 3 and in both the hydrogen's making 1. So this is better simply because the number of bonds being made per atom is what they usually make. Now, why do you think those, in a very loose explanation of why they tend to make only that many bonds, the explanation would be, well, if most compounds that have oxygen in it has oxygen with 2 bonds, it's because that's the most stable number of bonds for oxygen. Okay, so here, why can it make 3 and 1? Well, because you can still have an octet, but it's not as stable. So between these 2, this is the most stable. This is the one you choose. Okay?
Okay.
So the way we got to these 2 choices was this choice, I took this bond, this pair of electrons and made a bond. In this choice, I took this pair of electrons and made a bond.
Mm-hmm.
Okay, I think we might as well do D.
Okay.
So for D, we have oxygen plus sulfur plus 2 chlorines, which is 6 plus 6 plus 2 times 7. So that's 14 plus 12, which is 28 electrons. And we know that oxygen normally makes 2, 1, or 3. Sulfur usually makes 2, 4, or 6. And chlorine usually makes 1, 3, or 5. So we're going to choose sulfur as the central atom.
Because it can make the most.
Yeah. Okay, now we have 28 electrons and we've only used 6. So we put octets around here. And to get the octets, you put the electrons in as lone pairs. Hopefully, if anyone does watch this, they know never do this. If they're non-bonding electrons, I want to see 2 dots. I don't want to see what looks like a bond on the side of the thing.
Okay.
Okay, how many electrons have we used here?
$24.
24. So it looks like we've got to do something like this. We put the rest on sulfur.
Yeah.
So this sulfur is hypervalent, right?
Mm-hmm.
Now we're going to learn one more trick, and that's this. Why do I do that?
So the oxygen.
Gets its 2 bonds,
Yeah.
and sulfur gets 4.
Okay.
So this is what I would expect from our class. Okay, that was good. We did some of the evens from the back of the chapter.
Okay. Thank you.
You bet. You have a good day.
See you tomorrow.
All right.